Hello and welcome to this video. My name is Alex, I'm an international welding specialist, welder and mechanic from Germany. Today we will be talking about welding cast iron. Welding cast iron is a mystery to most people, as some even say that it is impossible to do. Well, that's not the case, but it can really turn into a nightmare. I'll try my best to explain everything as good as I can, but this is a huge topic and I think you could talk about this for hours and hours. So if you think that I'm missing something, that you want to add something, or that you got a good amount of experience and want to share your wisdom, feel free to do so in the comments below. So I felt that there is a need for this video, as this video will not include a brand new frying pan made out of cast iron with an intentionally broken off handle, because I think that this is not very realistic and doesn't really fit the reality that most people will face when they try to weld cast iron. The items that we will be repairing in this video come from very different eras of cast iron production, therefore we got variations in casting quality as well as contaminations in the parts because they have been in actual use over a long time span. A quick disclaimer, I don't have the most glamorous arc shots in this video. I always tried to get the camera as close as possible, but since I wanted to get some work done, the camera wasn't always my first priority. So we will start off with this Chicaba drill press vise. Then we will move on to this cast iron pulley from my Cabietti Mario lathe. It is from the 1940s. And finally we will be repairing this cast iron saw arm of a metal hacksaw. So let's start off with this Chicaba drill press vise. This was made in the, I'm guessing, 1970s, 1980s here in Germany, and yeah, this is just a very standard drill press vise. Somebody did a very good job of drilling into the guideways, and this is a very common problem. There is no financial aspect in repairing this, but this for me rather was a good study piece to get some first-hand experience in cast iron repair welding. Since I wasn't sure if this is really cast iron, I first of all did perform a spark test, and therefore I just took my angle grinder and just ground on the edge of the workpiece and compared this directly to a piece of steel. It turned out that this actually is cast iron, but it doesn't seem to be like the regular gray cast iron, so I'm guessing that this is ductile cast iron, which matches up with what the manufacturer claims. They say it is some kind of a special cast iron, whatever that means. Anyway, after welding I had some significant hard spotting, so I'm very sure that this is cast iron. First of all, I punched out the old epoxy that somebody has filled up the holes with. This wasn't doing anything at all and it was kind of a redneck repair anyway. So next I took my angle grinder and made a very good weld preparation. This included a lot of grinding, and I later on switched to a smaller hand grinder with some grinding pins to reach in all the areas. And I had to take out a fair amount of material to really be able to lay down some nice beads in there. So with the welding preparation done, I just placed the drill press vise in my mini baking oven, and please note that this is not a microwave but rather a real baking oven, just in a smaller form factor. Now, as the workpiece is heating up, let's talk about all the theory that lies behind welding cast iron. So, since I'm living in Germany, the following definitions may vary due to national standards and stuff like that, but I think you will get the point. So, cast iron and steel are both made out of the same ingredients. They both are an alloy of iron, Fe, and a certain amount of carbon. So in the process of steel making they take iron ore and coke. They put that into a big smelting furnace and then they put this on fire. This gets very hot and the stuff that drops out in below is called pig iron. So pig iron is a very brittle material as it contains way too much carbon and therefore is absolutely useless. So what they do is they take a big pot, they fill it up with a pig iron, and then they got something like a pipe and they blow oxygen in there. This stuff starts bubbling and boiling, and therefore the carbon in there starts burning, and its percentage in the whole solution is dropping. This process is also called the Linz-Donawitz process, or converter process, or BOS, basic oxygen steelmaking. So as you are reducing the amount of carbon in there, you actually end up in two areas. The first area is the cast iron area. Cast iron contains between 2.06 and 6.67% of carbon. And if you proceed further, you end up in the steel area. And steel contains between 0 and 2.06% of carbon. You may have seen this. This is a diagram which shows the amount of carbon and iron in the alloy that you are actually making. And everything to the right side of this line is called cast iron, and everything on the left side is called steel. Please note that cast steel actually is also on the left hand side. Therefore, the alloy actually is steel, it just was casted into some sort of a form. So next we gotta take a look at two types of cast iron. The most common type of cast iron that you will find out there is grey cast iron, or lamellar cast iron as it's also called here in Europe. It's called lamellar cast iron because if you would do a cut and edge, you would see something like this. The darker areas are just pure graphite or carbon, which forms out into something that is shaped like a cornflake. Lamellar or grey cast iron contains a very high amount of carbon, a very high amount of silicon, manganese, but the most problematic, phosphorus and even sulfur. Please note that these are the standards nowadays. What they put in there like 60, 70 or 100 years ago, nobody really knows. So grey cast iron has got some very interesting properties. For example, the great damping property of this material. And this comes from the fact that if you put some stress on there or some force, the force always has to wander around these graphite flakes, and this deflection actually helps dampening any sort of vibration. But also, therefore, the alloy is very brittle and absolutely not ductile. That means it just can handle a very, very small amount of deflection before actually breaking. The second most common type of cast iron that you will find out there is ductile cast iron, or spherical cast iron as it's called here in Europe. That is because if you would once again do a cut and edge, you would find something like this. So the graphite or carbon forms out into a spherical shape. And this helps this material to be less brittle and more ductile, therefore being called ductile cast iron. Once again, if you would put some force on there, you can see that the lines of the force actually have to be deflected a little bit, but not as much as with the grey cast iron. Therefore, this material is less brittle. Also, this contains much less sulfur and actually no phosphorus at all. Again, you never really know what they put in there like 50, 60, 70, 100 years ago. So these are once again just European modern standards. This doesn't say anything about what they put in there in the past. Welding is a craft, just like many others, that is easy to learn but very hard to master. The true craft within welding lies within a lot of knowledge, experience, good hand coordination, but most importantly in reading the puddle. I am by no means a master of this craft, but I'm trying to get better at this and learn every day. However, when you weld something you can always run into trouble, and this whole trouble aspect in the world of welding is regarded by a term that is called weldability. The term weldability is pretty much self-explanatory, and it just determines on how weldable a specific weld joint is. this has no unit, but it's more of a qualitative aspect that you're looking at. This includes the material, the process, all surrounding factors, like can you even access a certain weld, which process are you using, which material are you welding, in which position are you welding, yeah, stuff like that. However, as far as the material goes, we can break this down to the amount of carbon that is in the base metal that we are trying to weld. Therefore, we can either look at the pure amount of carbon in there or at the CEV, the carbon equivalent value. So the carbon equivalent value is there to pretty much calculate if a certain steel base metal is actually weldable or not. We also have the CET, which stands for carbon equivalent Thyssen, and this is used to determine how much we need to preheat a certain material if the CEV says that it is not weldable. Unfortunately, both of these values have very strict boundaries, and with the high amount of carbon in the cast iron, we are far out of. When we weld a certain material, we always heat it up to melting temperature and then cool it down back to the solid state. Therefore, we always run into the risk of hardening the steel or cast iron metals. In hardening, what you actually do is you change the atomic alignment structure of the steel by heating it up, and so above 723 degrees Celsius plus you get austenite, and when you just slowly cool that back down to room temperature you get ferrite again. However, when you cool that down too fast, for example by quenching it, you will end up with something that is called martensite. And martensite is a very hard and super brittle material. So what happens on the very fast cooldown process is actually you sort of get some distortion in the atomic alignment, as the atoms want to get back into their position they want to be in, but since the metal is already cool, they are forced to be in some sort of a position they don't really want to be in, and that mostly is the case for the carbon. And this is why hardening is highly depending on the amount of carbon that is in the steel or cast iron material. Okay, so one big problem with a crack actually is that a crack will always automatically grow bigger. Let's say we got a workpiece that's fixed on one side and we got a little crack here. As we apply a force in this direction, the force will actually run through that part pretty evenly, something like that. But as the force is hitting this crack, it has to reorientate to walk around the crack, and therefore inducing a hot spot here where you got a very high force in a very small part of the workpiece. This will cause the crack to automatically grow bigger and bigger and bigger, and you will once again end up with two pieces. So one of the biggest problems that we can run into when welding cast iron is hot cracking. Hot cracking will always occur when the metal is turning from the liquidous state back to the solid state. The main reasons for hot cracks are external stresses while cooling down or welding, and ingredients in the base metal that have a lower melting temperature. For example, sulfur, phosphorus, zinc, tin and copper. So now we know how complicated this all can get. What we need is a valid solution for all of these problems in order to avoid any kind of damage during welding or in the aftermath. Well, in order to do so, we got to talk about thermodynamics and heat management. Our main goal is to avoid any kind of rapid temperature changes, and that is achieved by preheating the part, therefore also reducing the delta T, so the difference temperature between the base metal and the molten metal or the heat affected zone. So in our case we got three main ways of heat transfer: conduction, convection and radiation. So let's take a look at conduction. Let's say this is our workpiece and it's resting on this table here. The workpiece is heated up, and what will happen if I place it directly on the workbench is that the heat will be drawn out in all directions into the workbench by thermal conductivity. The thermal conductivity rate is actually defined by the delta T, so the temperature difference between the two pieces and the contact between them. So if you would take a look at it from the side, it would look something like this. So convection, on the other hand, means that the hot workpiece that is resting on the surface here is actually able to create a significant airflow. The cold air from the room that you're working in is getting in contact with the hot workpiece, is heating up and then moving up, and is once again replaced by some very cold air from the surrounding room. This will significantly cool down your workpiece. If we take a look at the cast iron pulley that we got here, you can see that the grooves that the belts ride in actually can act as some sort of a cooling fin. Therefore, the convection side of things is actually very significant in this case. So the radiation aspect of things is that every hot object actually sends out electromagnetic radiation, which in this case is infrared radiation. And this is sent out to all directions and therefore losing heat. One other thing that I would like to talk about is how I call it, the internal conduction side of things. Let's say you heat up this area with a torch and make it very, very hot. What will happen is the rest of the workpiece is actually very cold, and therefore once again it will drag out all the heat from this zone to the rest of the workpiece. So how do we contain the heat? Well, the first idea is to put just something underneath that has a low rate of thermal conductivity and then putting the workpiece on top. Like for example this piece of wood. In order to stop radiation and convection at the same time, you can use basic aluminum foil. These are just multiple layers of aluminum foil, crumbled up a little bit, and this will serve two purposes. First of all, the radiation will be immediately sent back by the shiny aluminum foil, and the small air cushion in between the layers of the aluminum foil will have an insulating effect on the workpiece and therefore containing the heat in there. We also have to talk about the heat input by the welding process that we're using. We will be using stick welding and TIG welding, and both of these processes induce some heat into the material very locally and very concentrated, especially with TIG. That means that we have got to be sure that we don't overheat it locally, and therefore we can only weld in small increments. And small increments really means like maximum 50 millimeters or 2 inches of welding, and then you gotta stop and start welding somewhere else to minimize the local heat input. So other processes like oxyacetylene welding have a big advantage in comparison to TIG or stick welding, as they induce much more heat overall but less concentrated in one spot. So as you're actually welding with the oxyacetylene, you are also stress relieving the surrounding areas and putting in some heat there. So that means that the cool down process in general is much slower, which in this case is a very good thing. Yeah, so last but not least, we gotta make sure that our workpiece is actually cooling down properly. And we want to make the cool down process as slow as possible. Therefore, it is a good idea to wrap it in some aluminum foil and, I don't know, maybe put it on something that is very insulating. Maybe a sand bath, maybe you can put it back into the oven where you heated it up. whatever helps to make the cooldown as slow as possible. And by as slow as possible, I mean hours. Many hours of slow cooldown will help the workpiece to relax and end up without any cracks. So let's talk about the welding electrodes that we are going to use. These are nickel welding electrodes. There are two types of nickel electrodes. This is a pure nickel electrode, and then there is a nickel iron electrode. The pure nickel is designed to lay down a base layer and has a very good tendency of binding to the cast iron. The specialty of the pure nickel is that it will not pick up any carbon from the cast iron. So the nickel iron electrode is designed to put down like the third or fourth layer of welding, so you are actually quite far away from the cast iron, or you want to weld cast iron to steel. Let's say you got a workpiece like that and it's cracked off here, so you want to replace this side of the part with steel. You can use a nickel iron electrode to weld cast iron to steel. So as I've said, you can't really use the CEV or CET to determine the weldability of cast iron. Well, there is something you can use. This is the SCHAEFFLER diagram. It was invented by Anton Scheffler in 1949, and it is designed to predict the weldability of, for example, stainless steels, but also cast iron materials using nickel filler rods or equivalent stuff. So I'm not going into detail about how this exactly works, but let's say you have two different base metals that you want to join together. You got a base metal 1, and you got to find the nickel and the chrome equivalent of this base metal. And you got a second base metal, also find the nickel and chrome equivalent. You mark the 2 points, you draw a line in between. And then you find the exact middle of that line. And now you got to find the nickel equivalent of the filler metal that you are using. In our case, we are using 100% nickel, which has a nickel equivalent of 100%. We are once again far out of boundaries here, but I'm just gonna mark it so we can pretend like we could actually use this here. I'm gonna draw the line down, and now you have to guess how much dilution you will get between your base metal and your filler metal. Since this, once again, is just guessing, we will definitely end up in this area up here where it says A. So everything above this red line that I just marked is very sensitive to hot cracking. So on the other hand, you got this area over here. And this whole area is sensitive to hardening and therefore cracking. So you definitely don't want to be in this area, and we will definitely end up in the area of hot cracking, which is not as bad as it sounds because we are actually preheating and therefore have good control over hot cracking. Although we might not be able to avoid this entirely, but that's the best we can do. So there was a lot of talking and a lot of theory. But what is the conclusion of all of this? Well, you gotta preheat your part to at least 150 degrees Celsius up to 300 degrees Celsius, whatever that is in Fahrenheit, and you gotta use nickel filler rods. It's a very good idea to wrap the part into something, maybe put it in a sand bath, and try to contain the heat in the part as good as possible. Also, try to minimize the local heat input and only weld small steps at a time. Right after welding, you can also use a peening hammer or your chipping hammer to make little dents in the surface. As the nickel is shrinking down, by hammering it or peening it, you spread it out a little bit and therefore counteracting against the force that is induced by the shrinking. My personal advice would be don't get carried away and don't lose your focus. It is very easy to do so, and this will immediately kick back at you. You can lay down one bead and it's gonna work just fine, and the next bead is gonna be trash because you hit some kind of an entrapment and you will run into serious problem. But where does this leave us? Well, the success rate is at roughly 50%, and some say it's even less, and I would agree with that. it's very frustrating. But that's the hard truth, and that's all that I can tell you, and that's everybody will pretty much tell you. You just gotta see it that way. The part is damaged and therefore useless anyway, so you can try to repair weld it, and it's either gonna work or not. If it's not gonna work, well, at least you tried. And getting a new part usually is much more expensive than repair welding it, so it's always worth the try. So let's talk about safety. When welding, you always want to wear your certified welding helmet, a flame-resistant jacket or flame-resistant clothing, and also you gotta watch out for the welding fumes. Welding fumes in general are cancerous and will hurt your body very bad. However, nickel welding fumes are a whole different level. They are very, very toxic, and I can only recommend working under a fume extraction system and also wearing a respirator. I'm wearing this one, it fits under the welding hood. It has an FFP3 filter, so I can always feel comfortable when welding and position myself how I want to, so I don't have to fear breathing in this toxic stuff. Before welding, I used an infrared thermometer to check the temperature. This is not 100% accurate, but that is all I've got. The part is placed on these two pieces of U-shaped sheet metal, and this is just for insulation purposes. Of course, it's better to wrap the part or maybe put it on wood, but I actually didn't have a fire-resistant blanket on hand, and I just decided to weld 2 to 6 weld beads and then put it back in the oven for a few minutes. First of all, to keep it at working temperature and to help it relax a little bit more. What you can see, but mostly here, is that the nickel rod runs very poorly. They do cut out a lot, and it's very hard to maintain a stable arc. Although cranking up the amps helps this a little bit, the manufacturer instructs you to keep the amps as low as possible. Anyway, in my experience, it helps to increase the arc length if needed to prevent the arc from cutting out. And once again, please note the welding fumes are highly toxic. I'm working underneath the fume extraction, and I'm also wearing my respirator underneath the welding hood. Immediately after finishing a bead, I took a slack hammer and hammered the bead. This is also called peening. This is very important as it's releasing some stress that is induced due to the rapid cooldown of the weld bead. Once I was finished with all the welding, I put the part back into the oven and used it to slowly cool down the part back to room temperature. Here you can see the final result, and please note that this does not look good at all. And that's actually also not the point at all. These nickel weld beads will always look like shit, and this is just something you can't do anything about. I'm not saying that there is no room for improvement, but don't expect some Instagrammable weld beads. So one of the awesome properties of nickel is that the weld beads are soft and can be easily filed or machined. Please note that the cast iron base material can have some areas that might have hardened up, so this can very much hurt your files or destroy them, so keep that in mind. I used a big file to shred off most of the material and then used the edge of an angle and some smaller files to get the guideways flat and parallel again. Later we threw the part on a surface plate and measured the total distortion, which was 0.2 millimeters, which is surprisingly low. And we then threw it on a milling machine to true up the bottom of the vise. So this was a very good opportunity to resurface the bottom side of the vise, since it wasn't flat in the first place. So here is the finished result, and I'm pretty happy with how it went and that the vise actually is still intact, didn't crack or anything else bad happened there. I know that the welds don't look that beautiful and the guideways are not restored to a flawless state, but actually that's not the point at all. For me it was just mostly important to seal up all the holes and make clamping of smaller parts possible again. Remember, this is just a drill press vise, not a milling machine vise, so yeah, like tolerances and stuff are not that important. I even actually left out a small mark in the casting since it wasn't actually doing anything and not harming the part. The jaws just have a very small step where they rest on the guideways, so this is not critical at all. The next task was this cast iron pulley that was severely damaged and was eating out the belts. This is a part of my Cabiatti Mario from the late 1940s, made in Torino, Italy. But this will be a separate video if you're interested in that. So first of all, we will start off with a penetration test of the part. Okay, so 10 movements are over. Let's start with the cleaning. I'm And I don't know much about it, but the only thing I know is like you gotta take a towel and wipe off the excess, and then you use the dedicated cleaner to take off all the excess paint. And you don't spray the cleaner on there directly, but you spray it on a towel, and then you start using it to wipe it off. Okay, so first of all, let's start with this side. I think that's pretty clear that this is okay. Like, there's a little piece of towel sitting on there. You can see it's got a little bit of a pinkish color in general. Like, it's not a brilliant white, but a little bit pink, like like the penetrating fluid. And I think that's because the surface quality isn't that great. And I couldn't get all of the paint out with my towels, so yeah, I think it's okay. What you can see here on this side is our reference, basically. This crack was visible with the eye, so it was 100% clear that there would be a crack, and as we can proudly see this crack here, we got a reference that the procedure, how we did it, was basically right. And just add a little bit down here, because there was not much white or pinkish color down there. Yeah, so it was 100% clear that this would show up due to the high porosity, and yeah, I didn't clean the cracked surface here, because how am I supposed to? Like, it's not possible to really clean it up. There's another corner that was pretty much cracked. The part where I was worried about most is like the inside diameter where the belt is running on this pulley, and I actually was worried that there might be some kind of crack that is sitting right down there in the corner. Like, there's a small radius, and since this casting, as you all can see very well, isn't like the good quality that you would achieve today, I was worried that there might be a crack down there. Yeah, basically it isn't, so that's good news. Next, I used my small hand grinder to clean up the cracked surfaces and grind out the crack on the side face. See that? That's the end of the crack. that I didn't hit, but everything else looks good. Yeah, and the crack is gone. Like you still can see a little bit of that pink color, but the crack itself is gone and it's not going deeper. It's just a little teeny tiny spot, but that might be the general porosity of the part. Like I think we can grind deeper, but we're gonna end up with like grinding the whole thing apart, because there's always gonna be some porosity in cast iron, especially in this quality of cast iron. For better heat management, I used an old ceramic flower pot and some sand. As the sand was a little bit wet, I used my oven to heat it up and remove any moisture, as the moisture will actually cause big trouble during welding. So as filler material we are actually using the same nickel stick welding rods that we used before, and in order to prepare them I just used a hammer and some sandpaper to remove all of the flux and make absolutely sure that you get rid of everything, as it will contaminate the TIG welding puddle and therefore just cause much trouble. As the sand was in the oven, I used the time to dry test and set the position, and I think that this is absolutely important to find the right position and be comfortable during welding, because there will be no first prize for welding something in an off position if you don't have to. Like, work smarter and not harder. On TIG welding you should always follow a few things. First of all, I always started and stopped the weld on the nickel filler rod, and this was just to reduce the stress on the cast iron. TIG welding this is very hard, and when the cast iron becomes a liquid or just melts, it is a very thin liquid and it's almost like water. The nickel, on the other hand, has a much higher or thicker viscosity, and therefore doesn't behave like a normal filler rod. It will not flow anywhere and it will not wet in everywhere. And laying down the first layer is the most critical thing. Laying this down and getting the nickel to really wet into the cast iron is just very difficult, and you actually want the two materials to really melt into each other and not just being two layers on top of each other. When the first layer was successful, it gets much easier. What you will definitely experience is that you will get some undercut. This is not a real undercut, but rather the cast iron collapsing or peeling back due to porosity and the general properties of the material. And this is very hard to avoid, and also this is absolutely random, so you can't control this very good. Anyway, you will not prevent the undercut 100%, and if it's something that you personally think you can live with, don't try to avoid this, because you will end up chasing your own tail. This will not stop unless you covered everything with nickel, and yeah, therefore some undercut is okay. Another thing that you will see in the video, but is actually not visible under the welding hood, is the burning carbon. And you can't do anything about this as well, but these sparks will dull up your tungsten very quick. So you have to resharpen a lot, or just prepare like 5 or 6 sharp tungsten electrodes so you can quickly change them out. And my personal tip would be just take a drill and make resharpening with that on the stone much easier and more consistent. So it's been roughly 1.5 hours since I left it. We still got 115 degrees, and there I put the aluminum blanket on there to keep the heat in. So once I was done welding, I once again used an angle grinder and my small hand grinder to rough out all the shape, and once again the final machining or final material removal was done by hand, just using files. And this is very controllable, and the end result turned out absolutely flawless. The run out of the part is very good. Yeah, so if I would have a lathe on hand, I would do it on the lathe, but since mine was actually missing a pulley, so I couldn't do it on there. I had to do it by hand. So here you can see the end result, and I'm very happy with that. You can see the undercut that I was talking about, and you can actually see how random it actually is. At some places you don't have any, at others you got a little bit more. And you can also see the porosity, which some of these pores actually are porosity, which is unavoidable. And on the other hand, you got some fake porosity, which comes from peening. So there wasn't actually enough material, and you can see the mark which comes from peening the weld bead in the final result. So what you're gonna do about that, yeah, it's pretty much not avoidable. Yeah. Anyway, I think this is a good end result, and as long as this pulley will stop eating out all the belts, I'm happy with that. So far, both repairs went very well, and in the following I will show you how easily you can run into some serious trouble. So this is the arm of the saw, and it came back from sandblasting, and you can see even better now that there is some severe damage to this part. This is the part where the two linear guideways get pushed in, and as you can see, it's cracked here. It has got another crack that's running here, and one more crack that's running here. That's the outside. The inside is even worse. You can see, actually you can see, there you can see that the cracks are actually adding up to one big crack in the middle there, and they are running much longer than is visible from the outside. Crack goes up to here about. So we're gonna do a penetration test and see what this shows up. So we will drill this out. Well, the day that I welded the saw arm, it was roughly 0 degrees Celsius outside and it was very windy as we had some storms coming up here in Germany. And I had to heat up the part outside on a propane barbecue as it was slightly too big for my oven. And the trouble pretty much began with the first weld. The cast iron was very sparky and it was super cold in the shop, also around 0 degrees Celsius, and I was actually struggling to keep the part at a working temperature or actually get any good penetration into the root. But the biggest problem was myself, as I got way too comfortable with welding this and I was welding without peening the weld. Also, I didn't give the part some time to relax, as I was actually fearing that I might lose my preheat way too fast. But the point where it really got out of hand was when the first layers of nickel were laid down and I decided to use some regular steel filler rods instead of the nickel rods. And this method can be used to build up more material, but in this case the problem was that the C-shaped area of the part was allowing the steel filler to induce some massive tension on the cooldown. Therefore the part just cracked in the exact same spot.
Fuck. So we have a crack again. Same fucking spot. Just starts there. I don't know how deep it goes, but yeah. Cracked all the way through. Well, this took more than 1 hour in welding, and yeah, took less than 5 minutes to remove it. So I'm finished. I just wrapped up the saw arm in 2 t-shirts and this welding jacket, and yeah, just gonna let it cool down a little bit. I put it in the oven for 5 minutes or on the grill for 5 minutes to chill out a little bit, and now we cool it down slowly. So yeah, that's gonna take at least an hour, and yeah, I think the result is quite okay. I'm not too happy with it, but I think it's not cracked again. Whatever. I think we gotta see.
So we are back in the workshop, and unfortunately we don't have much luck with our welding. It cracked again, so this is what can happen. Fortunately 50% of the weld was okay. I did a penetration test, and yeah, it first showed up when I was grinding it down, because the nickel chips were actually forming a line across the edge of the weld, so that usually indicates that there is a problem. Yeah, the workpiece is on the grill again. Today it's a little bit warmer, although I can still think you can tell from my breath it's a little bit cold, so just 5 or 6 degrees in here. We will try our luck with stick welding again. The rods are in the oven at 150 degrees to get rid of any kind of moisture in there. And the workpiece is preheating on the grill. And yeah, we will come back in a few minutes to weld it. So as 3 times seems to be the charm here, I just gave the part much more time to heat up on the barbecue. I also wrapped it in more blankets, and actually it wasn't that cold and especially windy on that day. The decision to switch over to stick welding was just right. I preheated the stick welding electrodes in the oven to 150 degrees, which also helped it a lot. And I just got the feeling that wetting in the nickel to the cast iron was working much better. I had immediate success, so I could really lay down a first layer and really lay down a good root, which was very important in this case. And yeah, overall I just got the feeling that stick welding is something that I would always prefer over TIG welding, because the nickel and flux combination seems to help the nickel to really wet in and just mix up with the base material. So the overall result of the first layers, which was significantly different and much better overall. Also, I just took my time and used a grinder to sometimes just re-grind the bead that I just had put down. So I was actually forming always optimal conditions for the next bead layer that was coming next. So this is the final result of the Hacksaw Arm. Yeah, that was kind of a pain, but it worked out in the end, and yeah, so far I'm pretty happy with that. Doesn't look too pretty on the outside, but I think the overall structural strength of the part is back to a working condition. I used a Dremel to clean out the inside. Sorry I didn't film that, but this fine nickel dust really just destroys my cameras, and I already have one camera that is barely working at all. And yeah. So yeah, overall, she ain't pretty, but I think it's working, and that's everything that counts for me. We're just gonna put a big layer of paint on there, and yeah, that's gonna be good enough. I test fitted the linear guideway. I still have to take this down just a little bit, but I'm gonna do that when I finally reassemble this to make sure that I just get a decent fit in between the two parts. Well, and as I can already hear people screaming, oh, welding has warped this diameter and it's not gonna fit anymore. Let's see. There's the keyway. Better clean that a little bit. So I call that a snug fit. So if you want to see more about this lathe, I'll do a whole restoration video project about this. I don't know when I finally will be releasing the videos, but yeah, stay tuned for that. So thank you very much for watching this video. I hope you enjoyed it and you could learn something from this. If you got any recommendations, things to improve, or anything that you want to add to this topic, please feel free to do so in the comments below. And yeah, thanks again. See you next time.